Less than 10 seconds.
Have you ever wondered if there are parallel universes?
Worlds either entirely the same or completely different from our own.
This month, we're going to be talking about a topic that has recently had a resurgence in pop culture and quantum physics research alike.
The multiverse! I'm Marley, and I'm the astronomer here at the HR Macmillan Space Centre in Vancouver, Canada, on the unceded territories of the Musqueam, Squamish, and Tsleil-Waututh Nations.
And I'm Mily, and I'm a filmmaker, scientist, and the multimedia producer here at the HR Macmillan Space Centre. And together, we are your hosts of a new monthly show looking at the cosmically cool theme of the month here at the Space Centre and exploring it with some science chats, some demos, and experiments.
Welcome to Space Jams!
When scientists discuss the multiverse, they're referring to the idea that outside of our observable universe, the universe that we can see and measure, other universes might exist. What these universes look like and how they came to be, we still don't know. But there are three major theories of the multiverse in quantum mechanics and cosmology.
Because these theories are still just theories, it's hard for us to do demos for you to show you what they would look like, at least without some serious advancements in technology. So instead, we're going to give you an overview of each of the three and provide you with some more resources so you can dive into some more depth if you want to.
Like giant, deep, dark, math and quantum physics-filled swimming pools.
We love the analogies here at Space Jams. The first theory we're going to get into is the theory of bubble universes, which relates back to a theory called eternal chaotic inflation. In cosmology, which is the study of the origin and development of the universe, a major theory for the beginning of our observable universe is the Big Bang, a moment where a singularity, which is a point of infinite density, exploded outwards and rapidly cooled, forming the early universe. After this Big Bang, certain properties of the universe we live in started to form as well. The preference over matter over antimatter, the divisions of dark matter, dark energy, and regular matter, the building blocks of the universe we are only beginning to understand. But what existed before the Big Bang? This is where the theory of eternal inflation comes in. This theory says that our universe formed from a quantum fluctuation in some region of space-time. The chaotic part means that this expansion could happen at any point, if that point had the right conditions. The eternal part of eternal chaotic inflation means that this could go on forever. Different places in space-time could start to inflate, grow, turn into bubbles, maybe even pinch off as things go on. When these parts of space-time expand faster than the regions around them, they have a chance to kind of pinch off and create their own bubble universe. So our universe could be in a bubble just like that, created by our own Big Bang. And in different regions of space-time, there could be entirely different universes, each in their own bubble.
The second multiverse theory is one that is often used in movies, books, TV shows as a plot device, the many worlds interpretation of quantum mechanics. To understand the quantum physics side of this theory, we first have to introduce the concept of the wave function. The wave function is an equation that can tell you the probability of measuring a certain particle or quantity at a certain time in a certain space. It's often explained in the context of trying to locate an electron. The wave function will tell you the probability of finding an electron, which is very small and very fast, at that point in space. If you were to check to see where the electron was and measured it, then the wave function collapses, and the electron is in one of those places. In other words, before it is measured or observed, the electron could be in many different states. But when it's observed, it's in one state. A really cool experiment that gets into how truly weird quantum states are and how they are affected by observation is the double slit experiment, which we have provided some links to below. In the many worlds interpretation, the wave function is applied to the entire universe. There is a universal wave function, which is the quantum state of the totality of existence. But when a measurement is made, it does not collapse, meaning that all other probabilities or every other quantum measurement exist in other universes.
To go back to our electron, even if you measured it to be in one location, there is another universe or alternate reality where it is in a different place, a different state.
Alternate realities are often used to establish the multiverse plot in telling science fiction stories. A key plot point is changed, and the story follows that other possibility.
These different universes originate due to points of divergence. An example of a divergence is an event that can have different outcomes, which then causes different universes, one for each outcome.
The third theory of the multiverse is derived from string theory and the concept of extra dimensions.
String theorists have proposed that the universe we think of as our universe is just a three-dimensional surface, or rather 4 dimensions when we factor in time, embedded within a larger universe with 9 spatial dimensions.
A way of thinking about this is if we were to draw a stick figure on a piece of paper. The stick figure is flat. It only experiences life in 2 dimensions, up and down, left and right, the y-axis and x-axis in graph talk. But there is a third dimension, the z-axis or depth, which 3-dimensional objects have. We experience this third dimension, but the stick figure in their 2-dimensional world couldn't perceive this z-axis at all. String theory postulates that there might be more dimensions on top of ours that we can't perceive, just like the stick figure can't perceive depth. All of the theories that we talked about today don't have any experimental evidence to support them just yet. Just a lot of theoretical research, which made it kind of difficult to collapse down into one Space Jams episode.
Collapse like the wave function. If you want to dive deeper into the waves of some of these theories, including the many worlds interpretation, eternal cosmic inflation, or get wild with some string theory, we've put some links to some lectures with some amazing quantum physicists and cosmologists down below.
Thanks so much for tuning in, and we'll see you next month with a brand new Space Jams episode.
See ya!